So now we have Bruno Vergara that is going to talk about the eigenvectors for the operator.
Thank you, Benoit. So basically, I would like to continue with what Adam started this morning. So basically, the idea would be to understand, well, the goal would be to understand the decay of the kernel at some point, but for now, I would like to show you at least what we think is a good approximation of the true eigenfunctions by some special functions that are going to show up here and that you're seeing in Mathematica now. Just to remind you a little bit what is the equation, and the way that I'm going to write it is going to be this way. So unfortunately, we have a different notation, but I think we can live with it. It's going to be that instead Adam had a h squared, and now we have an h cubed. But basically, essentially, when sigma was small, or when h was small, our h is going to be small as well. So there's only going to be a power factor, 1/3 or something like that. So
maybe your h squared is no, your h cubed is h squared.
Yes, this is exactly.
The power.
Yeah, exactly. So I'm gonna write it in this way. So y is gonna be his x coordinate. The reasons very colorful, so I'm not gonna explain them. But it's gonna be basically the notation I'm gonna use in Mathematica. So I want to be consistent between what I show you there and what I write on the board. So x is gonna be just y, simply relating. And therefore, the equation that we're going to see is the equation that basically Adam wrote. So I'm going to write the eigenfunction as g, and this is the equation that we want to solve. Okay. So the disclaimer, right, is that sigma squared is h to the cube in my notation. And before this was h squared for Adam's talk. All right. So, So in the previous talk, what Adam was doing, basically, the idea. I'm sorry that any of this is going to be recorded on the Zoom, but I'm sorry about that. The idea of previous talk was right. So even though I have a different parameter here, the turning point is at the same point. So it's, in my case, y equals to 1. So that completely agrees with the notation in the previous talk. So what Adam was telling us is that somehow he has an approximation of the true eigenfunction by a function that goes to some range of the parameter h bar in my notation to the left of the turning point. Right. So I think in my notation, that would mean that I can improve bounds on the error between the true eigenfunction and the approximation with a function in this regime between 1 and h to the power 3/2. Just trying to sort of unify what was told in the previous talk and what I would like to show you with the pictures that I have here in Mathematica. So what I would like to focus, at least for now, let's see if we have more time to discuss also what happens to the right of the turning point, but I would like to start at least to try to understand what could we do then. Because surprisingly, or well, this is something that we discovered a couple of weeks ago, this problem was already studied back in the 50s. And the people got a very good approximation here using Bessel functions. So this is the goal of my talk, to convince you that actually we can have a very good approximation in this regime, not just by doing the asymptotics of the true solution, but having something global, which is going to be a Bessel function. All right, so this is my goal. At least I think we can do it if we spend an hour or so, or even less. We'll see. So I don't think it's worth it if I go on the details of how we reparameterize the equation. Basically, it's going to be similar to what Adam did with his variable z or zeta. I don't remember exactly the notation. But I could, yeah. So what I would like to start with, let me go through my notes, is to talk about this kind of problem. So yeah, so first let me state what I want to prove or what I want to show you. So
Can you stop sharing and so then the camera will.
right, that is true. That is true. Good point. So stop sharing. Now you can see me. Wow, what a frame.
Yeah, it should be good.
All right, good. Thank you. Good point, then one. So I would like to. So the goal would be to just study, if you want, asymptotics. Of the function. Near the order. And as I said, the idea is going to be that we are going to get an approximation. Let me call it G naught. That depends on y. And up to some constant that depends on my h bar. And this is important. This is a difference of the way we were thinking about the problem with what Adam discussed in the first talk, is that for us, the measure is going to be simply the Lebesgue measure. And then we are going to get some normalization factor on the eigenfunctions. Okay, so that's somehow a little bit different from what you were saying, but in some sense, it's going to be equivalent. Right, so this constant accounts for that normalization. And then we're going to have something like this. So I want to show you something just to get a flavor of the kind of approximation that we have. So you're going to see things that are familiar, very similar to what Adam presented. And the new thing is going to be this Bessel function.
S the same as zeta.
So I'm going to, yeah, so let me just put it right. So the exact, yeah, I want, yes. So I'm not, I mean, I didn't know about their exact reparametrization. So I don't know the exact relation, but it should be very similar. I don't know, maybe there is you probably, Adam or Bruno, exactly if this is exactly zeta or it's minus zeta or it's a shift with a complex phase. I'm not sure. But it has to be something very similar to zeta in some sense, because it comes from the Langer transform anyway. So I don't expect something very different.
But so S is
I'm gonna
turning point.
Yes, so I'm gonna write what S is. Maybe with that we can figure out exactly what is the relationship. So let me write that here. So with S of y is just this function, so it's gonna be so I'm writing things very explicitly so that you can compare to what I wrote in the Mathematica notebook, and also to get an idea of how similar or different it is from what we saw in the first talk. So this is for y less than 1. So this should be, yeah, I have a bracket. Where do I have the bracket? So this should, and I have also using the bracket. So this should be very similar to what Adam did, because this is to the left of the turning point. So somehow this has to converge to your ideas. I'm not exact.
I think it's exactly.
You think it's exactly right? I doubt that would be anything different because we are doing basically.
Two centers at 1.
I'm sorry.
The turning point is at 1.
It's at 1, but also it was in Adam's talk, if I understood it correctly.
Yes, there's an axis up.
Yeah.
Zeta says 0.
Yes.
And then it's
Yep. So this is somehow, yeah, the turning point is. Maybe we can write it down. Sorry? And S, you are saying that agrees with your theta. Right, okay. The thing is that you can also do this to the right of the turning point, although I'm not gonna use it now because I would like to focus on the smaller problem of the asymptotics near infinity, but maybe if there's time, we can also talk about it. Yeah, so let me write in case you want to compare at the end with your work, this is what we got. And I'm gonna show pictures of this guy, so maybe we just need to wait a little bit to see how it looks like, but yeah, you can think that this is my S function.
So the second one is for y bigger than 1.
Thank you. Yes, this is what I said.
Because then it's minus.
Yeah, I guess it's minus it actually. Because there, I think the picture was completely the opposite with just a sign. All right, so as I said, even though we have worked in this region to the right of the turning point, as for the sake of, well, yeah, being a little bit short on what I want to describe, I would focus also to give you the details of what happens to the left of the turning point, so we have the full picture with this talk and the previous one. All right.
Like what is the SY? I mean, I know it's, but where the cutting point of the curve on the SY or
Here?
no,
Here. I don't know, we can ask Mathematica, but for us that doesn't play a role. So I don't know.
No, I just want to compare if S really is that SY.
Well,
Pi over 2.
yeah, I mean, we can read it off, right? We can just read it from here, right? I guess.
3 pi over 4 plus.
Exactly.
I think 0 is negative.
Okay.
Perfect. All right, so yeah, so my goal would be to convince you that this is the approximation near 0. Okay. And I think we have all the ingredients. So Y is like the X for the before, S is this reparametrization, and this is just yeah, maybe I should write that. But this is the modified Bessel function of first order. If you want with index 1.
Wait, just T0 is not an exact, it's not the eigenvector.
No,
It's
so
just eigenvector.
yeah, so right before I wrote G as the eigenvector, and I want to say that G naught approximation near 0. So it's to complete the picture of the Briggs talk.
So you can say what's more than 1 half.
So,
You can say what's smaller than 1 half.
right, let's say yes, we could say something like that.
And it's an approximation in the sense that
We are gonna have a uniform bound between the true solution and G naught in terms of H. Okay. But for that, yeah, I first would like to start like with the very basics of this. All right, so as I said before,
no, so
Yeah.
on the board in the middle.
oh right, yeah, that's a good thing. No. I will just, I just use my hand. Stuff I teach here, but somehow I always manage to get in trouble with the words. All right, so what I want to say, yes. So first let me start with how a little bit the story goes. Yeah. So I'm gonna start with this ODE. So it's a generalized version of what basically we want to study.
And then you call it few instead of you or something that because you're unknown a symbol that doesn't really resemble a value.
Right. Well, my reason for not calling it G, for instance, or anything close, is that it's not exactly what we want first. So, but yeah, if you feel that the notation somehow has to change, you can tell me. But you want field? Okay, that's good. Okay. And yeah, I don't know space. And of course, there should be a U multiplying this. Oh, sorry. So here's basically where the story starts. So I would like to consider an equation that it's a bit more general, but somehow already gives me what should the solution look like and how that is related to my ODE there. So you can see that we have some parameters. You can think that complex parameters at this level, everything is orthogonal. So you just take these parameters and the solution. Can be written as a combination of Bessel functions. And my Bessel functions are going to be of this form. So there is a weight to beta nu minus alpha, and then here I have the two solutions, the two Bessel functions. Right. So at this level, there is already a hint of what I would like to do, which is maybe the first thing that we could do, well, first thing would be to cancel out first order terms. So I would choose the parameter, let's say alpha, so that 2 alpha minus 2 equals to 0, so I don't see first order terms. I forgot something. Plus 1, thank you. Right.
So sorry. So you have written the second order of the unit. So
yes.
There will be a fundamental solution system of 2, and that corresponds to the J plus and minus with these powers of Y. Absolutely.
Yes, that's it. Which I didn't know that you had such a nice solution for this kind of equation, but as I was saying, this already gives us a hint of what we would like to search for, because I don't see now this first order term, and from here I get a y to the 2 beta, so I can choose beta so that I see the Coulomb potential, and maybe I can just neglect what we have on the constant here. This is somehow what I want to do. So
I'm sorry, just can you explain more, because you're going to look at this when y goes to 0?
Yeah.
Right. So now I'm gonna make a choice of beta and nu. and I'm gonna get an approximation of the true problem with this ODE. Right, so. Right. So this is gonna be like a first rough approximation. Then I'm gonna show you how close or how far it is with the picture of the true solution in Mathematica, so we get an idea. But yeah, so we choose, as I said, that, so that we cancel out first order term, and also we choose now beta between 1/2, so that we see the Coulomb potential there. And then I choose also nu equals to 1, so that when I do the expansion of the solution, I get the same asymptotics or the same linear asymptotics of the true eigenfunction, which I know a priori as a priori information. So
can you write down what you get after you substitute for all these things?
Sorry?
You can write down the ODE that you get after you substitute for all.
Yeah, so it will be this one. Yeah, precisely. I'm saying that y is small enough so that I can forget about the energy term, the -1 that I have. Yeah, that's precisely the order.
How you can see this alpha.
Yeah, but that was fixed from the first.
Sorry.
Yeah, so
the 2 alpha minus 3 beta u is going to give you minus alpha in the
Yeah.
on the right.
Let me think. What I have the choice to choose alpha equals to, so if I choose, let's see. So I have 2 beta, I said this, I said this, so this cancels, so I can choose.
You said beta to be 1 alpha, no to be 1, then the top of which gives you alpha equals 0.
Exactly, so I don't,
Then it's gone.
right, so I only have the Coulomb potential, yeah. Right. So this is like the alpha equals to 0, and then therefore,
Nu is equal to 1. Okay.
Yeah.
Good. All right. So
right,
would it make more sense then?
He wants alpha to be 0.
Yeah, would it make more sense if that means alpha to be 0, so that at the term of the 1 over y squared, you cancel the constant.
Yeah.
And so then you get the next term to be the right one.
right, yeah, whatever, in the way that you want to do it, in the end, I want to see this equation, right?
You want to do 0 extension, say,
Right, so I just want to see the ODE. This one. Right.
You're right now, 1 over
Oh, 1 over y, sorry. Thank you. Yeah. This is
It's like great.
right. It's gonna play a role, exactly. So this is roughly the idea, but yes, that's a great point. So actually, the fee that I get of this ODE is gonna be the square root of y, J1, and then gamma as I mentioned, and the square root of y. Okay. Right, but here somehow I also need to take into account the h cubed that somehow is not playing a role here. So for that, basically the choice that I have to make, and you can read it again from the ODE, is gamma equals to 2i divided by h to the 3/2. You see, if you plug that value there, you get precisely the ODE that I wrote on the left.
And I as in the imaginary number?
I the imaginary. So let's see in Mathematica, how close are we? Yep.
This -1 is important.
Yes, we are going step by step. Yes, but that's a great point because the next approximation is going to take into account that -1.
And
Yeah.
if you had the inverse, the attractive potential. then
Right, I will
you-
have not the I will have just Bessel's function. Yes, we can do the attractive potential in this fashion. Yes. if you allow me, then I will just share my Mathematica. So I'm gonna speak over it, but the idea would be to show you a little bit. I think, yeah, I think we are. I'm sharing the right screen, I think. All right, so here I have implemented the function is y that I said before. My true solution, again, for historical reasons, is gonna be called B on my notebook. I forgot to change the notation, but the rest of things there should be consistent. Yeah.
So the capital S should not be little in the second line.
Right, thank you. It's just that in the notebook I'm not using W at all, that's why, but that's a great point. It's another, again, for historical reasons. Yeah, I'm not using the W. I put it explicit that factor y to the power 1/4. I wrote it down before explicitly, so I'm not using it as a function independent. Right, so yes, so let me go to what I want to discuss. I have a few things going on here. All right, so this will be the first approximation that I mentioned. So here I recorded what is the asymptotics of the Bessel function. So it's just the argument raised to the index of the Bessel function. So you see that when nu equals to 1, basically at near the origin, I'm linear. So which is what we expect from the expansion of the true eigenfunction.
Well, what is B?
The true eigenfunction. The true eigenfunction. The Whittaker function.
So is it numerical or?
Is
that's your D is Whittaker M of whatever.
B is Whittaker M. It's just that has this funny name, but it's Whittaker M, and it's yeah, you see that in the argument I'm putting H because this is the way that it's programmed somehow, just yeah, to have control on the scale of H that we are putting there. And what you're seeing, so yes, so on blue is the true eigenfunction, the Whittaker M, and on orange you are seeing precisely this solution. So it is written in terms of the modified I Bessel function because I have a constant which is purely imaginary, right? Actually, I recorded what is the relationship between the modified and the Bessel, the ordinary Bessel.
Yeah, and can you tell, so this corresponds to what value of sigma?
So this corresponds to the value of H, in this case 0.2, and the relationship, if you remember, was sigma squared equals to H
so
to
that's,
the
0.089.
Exactly, this is where I recorded what is the value of sigma. Yeah. In all the plots you're gonna see is gonna be similar. On blue, it's gonna be the Whittaker M, and then the rest of things that I put on the plot are gonna be approximations.
And so sigma is 0.
Yeah. Yes. So you see, with this very rough approximation, as Professor Slack mentioned, we are not covering very well what happens at 1. Actually, I can go there. I can try, and then you see we have something that grows exponentially. Right, I'm not taking into account at all what's going on the turning point, but we're gonna be there. But yeah, very near to the origin, this is already enough because it's a sort of, you see, if I go, I don't know if the computer allows me, yeah, this scale. So actually I could go to the scale H.
0 sigma.
Yes, so yeah, I could do H. Here, the approximation is fair enough.
And so this is 0 sigma to the 2/3.
About 3 halves.
Well, sorry.
So, yeah, I can do it in my head. So
What-
this is 0 sigma to the 2/3.
Yeah.
Yeah.
But can you plot up the weights to the 3 halves?
Mm-hmm. So the approximation there is for a small scale, it's very good already. The problem is what Professor Schlack said, because now we lose all the control near y equals to 1. So we would like to incorporate that in our equation. So this is going to be the second approximation that I'm going to make. I think so far so good. Right. So the people were studying this kind of equation, this kind of ODE. So maybe I will put it ODE 1, and then I'm going to write a second ODE. That's a bit more general and would allow me to do what I want. The first ODE and the second ODE that I would like to discuss can be written in this form. So it's kind of ugly, so let me just write it in this way. So I'm gonna keep your notation phi for.
Or C if you want to add a new.
Right, you want to put another, it's just that I'm using C for something different.
the fees.
Yeah,
Just something that.
phi or phi tilde maybe.
It should not look like new, should not look like Y. That's all I'm asking.
All right, so but the y here is gonna be the same, so let me phi tilde, something like that. I don't know. And then I'm gonna put an arbitrary function that I'm gonna write chi. And I'm gonna take two derivatives with respect to another function that I'm gonna call psi. Yes, it's kind of ugly, but surprisingly, yeah, this is I think the magic of a special function. We're gonna see that it has a very similar solution to the previous one. So this is the second ODE that I want to study. So as I said, so see, y is just a reparameterization of y, so it's a real function. Some real function. And here, chi is going to be another function, but I'm going to choose it in some precise way now. Yeah, let me not say exactly now what it is. But yeah, let me put that in a minute. So
One very easy question. Your approximation, does it blow up one?
yes.
But no, I mean, like it's big, but does it go
So yeah, so that's very easy to see, right?
And it's exponential in 1/h.
Yeah.
Maybe if you just plot it, then at least we'll see.
Yeah,
Plot it between 0.5 and 1.
doesn't seem so, right? Nope.
No, probably.
No, it doesn't seem so. You see the first term is just constant, but what we'll see. Yeah, so Benoit was suggesting something interesting, which is, let's say 0.91. It's big, but not, yeah.
So it's exponential of 1/h somehow.
Yeah, we have it here, right, somehow, yeah. Yep. Can I continue? All right, so, but I don't want that, well, the second approximation is also gonna be sort of big at 1, but it's gonna be definitely good enough so that we can go all the way to y equal to, let's say, 1/2, which was already sort of worrisome in this scale. So you see that if I could go here from 0 to, let's say, well, yeah, the difference, although the scale, well, it's unfair to say because the scale is somehow normalized in a way that it's, but yeah, I could do that, yes, exactly. So I could plot the division. Well, yeah, that would be the difference in relative terms. But yeah, so before, if there are no more questions, let me just finish what is the solution of this. Is of the form the combination of this, well, actually, let me write it precisely. So I can write an explicit solution in this form.
And so the first thing you're trying to do is an angular transform to reparameterize the arcane,
Yes,
and then the guide is
right, but
not
so,
the same thing as for the language.
right, this is the conclusion that we are gonna get, that in the end, the side that I put is precisely the language transform. Yeah. So, but what I thought it was very interesting is that you can start actually with just basic ODEs and then find out that this fits in the exactly the framework that we already have.
It's completely magic. So, I just want to come up
This is already in a paper of the 50s. So,
by these crazy people. That they leave.
yeah, yes,
Fully special.
yeah, it's
Java, the good point is that you start with an exact, you can find by hand that when sigma is equal to 0, you get an exact solution. And then basically you're trying to continue this exact solution when sigma becomes positive. Of course, by positing that it's going to be more or less the same profile, but in change the outcome.
but to come up with something.
So then you conjugate to this sigma equals 0.
Why can't you try? I mean, for me, another thing to try is suppose that G is G0 plus something, or let's say G1.
Well,
Then you substitute into the ODE that you want to solve. And you get like some sort of integral equation.
right,
That's what we do.
yeah, well,
So
no, I don't think so. We don't. No, I don't think so. Yeah, no. No. Well, yeah, I don't know. But what I agree that it's magical is that you see that equation and this is the solution somehow.
So, ODE one,
Yeah.
very nice, and the idea that you ignore the -1 is great, because when y is very small, 1/i is much bigger than -1.
But that's the case sigma equals 0.
Well, but h bar equals sigma to the 2/3, so it sounds like you're taking h bar equals 0. You don't want to do that.
So that's it. But so once you restate it properly, the 1 is the sigma.
Yeah, I agree with Gabi that you build your approach, so you solve either multiplicatively or additively, right? Because the solution is not, doesn't have zeros until you hit the turning point. You can actually show that the solution B has to be strictly monotonic increasing from the monotonic so B until the turning point, until 1, has to be strictly monotonic. So you might actually be able to find the true solution by the one with -1 equals 0, G times a correction factor.
It's like that feels more intuitive. I mean, this feels fine.
Yeah, absolutely. But I haven't tried. I mean, could be that. Could
Maybe
be.
it gives the same thing.
Well, this is gonna be better, but by the picture at least, by the uniform bounds that that are already proved in the 50s. So yeah,
we can glue together what Hegel and Adam did. U and G works until from 0 to h bar to the.
Yep.
What is it exactly? So 3 halves minus epsilon. Adam wrote.
I guess it'd be.
So Adam had. In the rescaled variable, he could go to sigma to the 1 minus alpha, right?
Right.
So that G should work perfectly up to that point, and then we glue it together with the area.
The thing is that this sounds like a fantastic idea. It's already somehow done in the paper of the 50s.
I have no doubt and no clue that such a thing existed,
Yeah.
but can one read this paper? Is it a best?
This is what I did, basically cleaning it up a little bit and try to explain it to you.
Well, but did they write all errors in a form that Adam and Abraham multiplicatively one?
Not like that. Well, it is not written exactly like that, but we can read it off in some sense, right?
Because if you don't have that, you can't plug it into the equation. You need bounds and derivatives because when stationary phase, you have to differentiate everything in the energy. You see?
But you still start to do
Yeah, that's a good point. Yeah.
So that's why.
I mean, I think if you can get two good enough approximate solution, you get a parametrics. From the parametrics, you can easily get exact eigenfunctions. And then you will pieces. So
I think that what Adam was able to show
yeah, no, you need to have the right instead.
is what their equations they had is with one lambda, another lambda, you do it together at say equals 0, which is your S equals 0.
Yeah.
Right?
But there is one thing that I'm not completely sure about the strategy that you're suggesting, which is basically the problem at infinity somehow. Well,
Because you know that what you do is great because we know that you can pick up the x of x branch in the notation y of y. We have to pick up the analytic branch in y. That's uniquely determined with the and that's exactly the guy your best with J1.
right. So my question would be, so you have estimates on the error between the true eigenfunction and this Airy functions and with this error that you wrote in this way. So you're not gonna capture somehow the phase of because at the end the Airy function is gonna look like a cosine or a sine, right? So are you gonna be able to capture the phase there, or is gonna be the phase a problem when it's amplified by the evolution somehow, or no?
If I'm misunderstanding that, but so let's say we glue at sigma, the one and only sigma,
Right.
to the 1 minus epsilon. For
Right.
example, root sigma. So then we have to do together with AI and BI. What we will find with Gaussian is that the coefficient of BI will be extremely small. And basically only AI will come. You know?
This is what I don't think is true.
That's true, but
At infinity, it's not gonna work. So
Yes, there will be a phase shift, but shouldn't, we won't get an explicit expression, but you'll get an expression that maybe the symbol that I don't know.
So I have a picture actually of that. So maybe we can go exactly to this problem in 10 minutes. So I'm not sure. I'm not sure how I'm doing with that. But yeah, that it'd be great to know that, because if it is just like, as you're saying, like considering what Ebru and Adam did, like near the turning point, and we can glue these two things together, then it will be absolutely amazing. But I'm not so sure based on the picture. So maybe you can help me out to understand it a little bit better. But yeah, let me finish with this. So just to conclude with this ODE stuff. So I'm gonna set this guy function to be like this. And still amazed that all these things are gonna converge to something. If we do that, then the ODE is gonna become this one.
Is nu equal to 1 or?
Chi equals to 1 over psi prime, and psi to the 1 minus 2 nu.
But I thought we had said nu to be 1.
Not in this. You saw in the second ODE. Yeah. That is gonna be 1 in the end, but but I would like to start with something general to see, we arrived at the same thing that we wanted. Yeah, great point.
that's what didn't happen.
Yeah. So let me write the ODE. Just to continue with the magic if you want. I find amazing that someone wrote down the explicit solution of this in a nice form. So if you see this ODE, you already know the solution from now on. You can put it on an ODE course. So this is what you get if you do that choice of this arbitrary function chi. And voila, the explicit solution is gonna look like this. So we are already starting to converge to what I wanted, to very similar to what Adam wrote. So that is the solution. Well, I wrote the two solutions with the two indices here. And you see, this is somehow similar to the previous that I talked about, the first rough approximation. In particular, it has an I there, so I'm gonna see this as a modified Bessel function again. And yeah, so let me talk about psi here. Which should be the board that I want to use.
I think just this one.
So I just erased. So
Actually, you should stop sharing your screen.
right, that would be great. That's a good point. Then I will.
Well, there's that one board really up high. Can you bring that one down?
Yeah, I could use that one. Maybe here. Good. So what is the role of psi? So when I write, we want to write psi y equals to yeah, the way that I wrote it. I'm not sure if this is the right sign now that I'm seeing on my notes, but if it is not this, it's just very similar. Sure. I'm gonna see it on my one. So we knew some positive parameter, and C not some constant, right? This is how I'm gonna parameterize the arc length, and so I'm gonna do the choices. U equals 3/2, and nu equals to 1 in order match the asymptotic behavior of the true eigenfunction around 0. What is gonna be C naught? Just the Ackermann distance, right? This is what we expect. So C naught is gonna be the interval from 0 to 1, 1 over y minus 1, pi over 2. So you see what I have as a psi function is if it is not the same or it's just one sign different from what Adam presented in the previous talk. Okay, let me put that there. And right, so one thing that I haven't done yet, but I should, is to incorporate the scale h bar into the picture, right? I haven't done anything with that. So this is Bernie of writing the h bar everywhere on the ODE. Yeah.
So should C be minus that? Or
Yeah, probably. This is what I was. We can check it on the then in the mathematic, but yeah, I don't. I'm looking at my notes, and it seems that that's not there. Let me see it here. What is it written?
can you share your?
So actually, yeah, it's with the sign shift. Somehow I have it wrong here right now. Thank you, man. Yes. Right. So there was a change. There was a sign difference with
But if you, I mean, this is better if you keep the previous time, no? Because then at least it agrees with what is the zeta.
Right, but it's different from what I have in Mathematica, so I'm not sure if I want to do that. Yeah. I prefer to be consistent with my own notes, just in case. Right, so the story short is that now I can write with these choices, I can write the solution in this form. So now I'm incorporating the factor h into the picture. It's just that I wanted to normalize h to be 1 there, otherwise the notation is just too heavy. Yeah. Right, and this function, sorry, there must be an I here, yes. Yes, thank you. Yes. Right.
So now it's,
Yeah, so now again, I have a Bessel function with a complex, purely complex argument so that I can relate it again to the Bessel function that I wrote before. So this phi, I think I call it that, agrees with the very first formula that I wrote. This is what I wanted to convey here, that this is essentially, in case you don't remember, it's a constant that depends on h bar and up to this factor that I'm not going to write down, but now you know what the factor is or where that comes from. It's just this is square root of this psi over psi prime. And then we get the modified Bessel function. The argument is the Agmon distance 2/3. That's why we figure 2 half, 3 half, sorry, and then 1. Right, so this is where I wanted to end up. All right, so yeah, with this magic of Bessel functions, well, we get this kind of approximation. So let me show you how it looks like with the plot. So where should it be my?
and you have the same nice thing that if you apply your equation in P, you get some power of h times the potential times P.
Yes. Yeah. So
Okay.
so let me where I'm not seeing the zoom for some reason. It's not showing when I here. Okay. Where is it showing? Right here. I should be sharing my Mathematica. Yeah.
Yeah,
That's good. All right. So here I have plenty of stuff, but we don't have too much time. Maybe let me at least finish with this approximation. So this was the first one that I mentioned with the first ODE. And yeah, so this was what Javi suggested. This was the series that I wrote. Okay, so this is the second one. Here I have a picture of my reparameterization psi, which is going to be positive here, going from 0 to pi over 2. And you can see I did some series expansions.
Psi is what? Is minus, okay.
Yeah,
Psi is your
yeah,
new,
yeah. My new argument, yeah. So here I did some asymptotics. So you see psi basically is like near the origin is the square root of y, and then the prefactor that we get with the square root of psi over psi prime is again square root of y. So we have sort of the same kind of Bessel approximation that we have in the previous ODE, right? We don't expect something different. But here I'm gonna show you how it looks like the approximation when I plot in blue the true Whittaker eigenfunction, and now this second approximation. You can barely distinguish them. So this is a very good approximation up to all the way to 1. Actually,
Can you
How
go
does
a little
it
further?
which range do you want, sorry, Javi?
I don't know, bigger.
It's not gonna work, because then I would have to implement the S that it is, that the size built upon to the right of the turning point. The way that I program it here,
No, I mean.
Yes.
H to be 0.1. To 0.
okay. I thought to the right of the turning point. No, something is not working. Yes, the U, I guess. Yeah, here. Wow. Great that you asked. Here, I guess. Yeah, there. But this is something that maybe you expect, right? We are changing the scale here.
And if you keep H very small.
So it's gonna be very similar. So what do you like, 0.05?
Yeah.
It's gonna take some time, I guess. Yeah. I don't know what is the limit. Maybe Javi knows better.
No, wait.
It's just like that takes time.
So this is it.
So in blue is the true, and this is the second Bessel approximation. So this one, the one there.
So now.
They're on top of each
So
Yeah.
Can you plot the difference? So the U minus your B divided by B.
Mhm.
That's the relative error.
Right. Maybe, well, let's wait. If not, let me increase a little bit H. Or do a discrete plot. We'll see what they. Let's just wait. Should I stop it and put H a little bit larger?
Yeah, you could stop it into 0.1 or
Yeah, we could do that. Yeah, that would be.
0.5.
Yeah.
Oh. I just stopped it. I don't know what.
So this is not the answer.
I think it should be, but let's see. So you said from 0 to 0.5, and let me.
Oh, is that the answer? And then the part that I'm missing were things that it was trying to.
Yeah, it's exactly. It was just a numerical error. Let's see if this is a little bit faster.
So that shows that 1/10 of the percentage point down there is 3/10 of the percentage error.
Yeah.
They're very beautiful.
So actually this can be made more precise. So this is are the old papers of Erdely and Swanson. They have bounds, uniform bounds that depends only on sigma or H in that case. So that gives us, as Professor Lax suggested, a very good way to start with the decay, because now we can glue maybe the two behaviors together. So I have more things, but maybe I should stop, or Benoit, you just stop me whenever.
I think you want to understand that well, so I will give it continuing.
Yeah. So if you want, I could try to.
Whatever you have prepared. So
No, I have a lot of things here. I mean, we can.
that's great.
I don't know. We can discuss as much as you want, but one thing that I'm very interested in is what happens with this problem of the phase at infinity. So I would like to understand a little bit better. So let me go with that. So as I said, right. So I haven't. Well, maybe I have it here. Actually, I have it. So I have the implementation of the reparameterization S for all values of Y. So basically now I was working on to the left of the turning point, but yeah, so let's say that. So here, I hope I convince you that taking a Bessel approximation is going to be good here in this regime. And here, the work of Adam and Ebru shows us that basically we would like to use A. Right?
I'm on your picture, could you hope to go all the way to one? Is the basic function or? did you
No,
just
not really. Well, I don't think so. I think they're gonna be, well, you see the error is not super, well, it's not great, but let's see. Yeah, let's yeah, let's see if I can do this. I don't think so, but well, yeah, we have to check that. But what I would like to discuss or at least to understand better is what happens to the right of the term range. Right? Oh, again, here we have the error. Is that finished?
Yeah, but it dies before it reaches one.
Right, because yeah, the problem is that yes. So if I do this, I guess 9. Maybe yeah. Yeah, the SY is there. You can see that I think it's the way I defined it with a piecewise function. Piecewise function. Let's see. I'm not sure. So what is going to happen definitely with the approximation is that this function is going to turn complex, right? Yeah, the function is going to be real, I think, to the right of the turning point. Directly this one. I think it's going to turn.
So that is going to become complex?
Yeah, I think so. And for y, bigger than 1. I think that's what's, this is why I'm.
Yeah, but I mean, at least.
Yeah.
The simplest case, we need to be able to branch to.
Yeah, that could.
Agree at the turn.
Yeah, we could, maybe we could do that. Yeah, we could do that, yeah. This is not working. Takes a long time to go to that part of the plot. So well, it is what it is, I guess. So yeah, so at least we have a hope that here, I'm not sure if all the way to the turning point, but at least here we can match Bessel functions with the area functions, right? And something that I mentioned was that yeah, you could do S the parameterization to the right of the turning point. You can work with the area functions as Adam and Ebru said. And let me show you a little bit what are our findings on the same kind of problem. So here the function that I want to show you is this function G, the true eigenfunction of my ODE as before. But yeah, to the right of the turning point. So I'm gonna write it as a combination of area A, area B, and I have some prefactors that I call W, basically accounts for this square, no, the y over 1 minus y to the power 1/4. So that was also present in this formula here, the square root of psi divided by psi prime. So this is basically the W that you're seeing in the code. All right, so yeah, so here I plotted, yeah, what is the difference between the area function and the area function with this reparameterization. And what is more enlightening is this picture. So this is in blue, you are seeing the true eigenfunction again, and in orange, you are seeing the approximation with the area A. So near to the turning point, this is a very good approximation. So I can actually go, let's say, here, I don't know, 2. Right? So I wrote this with a coefficient A here.
But now,
yep.
So you convince us that A1 was the right thing to use. That I1, sorry.
Right, but because if I go, yeah, so.
Now you say that in fact area is good enough.
So what I'm saying is that area is sort of good enough, but it doesn't capture the linear decay at 0. So if you do the asymptotic expansion, you're not seeing it because yes, do I have here? Yes, run asymptotic expansion. Yes,
So it doesn't satisfy unity, but except for that.
exactly. Yes, that's surprising, but the area already it's a good approximation near the turning point, but yeah, doesn't capture the asymptotic behavior. I wrote that there just in case.
Just to understand, you mean it doesn't capture the boundary condition that R equals 0?
Yeah.
Yeah.
Yeah, you can never do that.
Yeah. Yeah, it's a
But
matter.
amazing that it's so good,
But it still is sort of not
I'm-
super far from being away from the the origin.
This kind of H.
So then you would just look at the relative error, because this area function is extremely small.
Yes, it's
Ah. All right, so yeah,
So what worries you?
I'm getting there. So actually, to what we did was to take the asymptotic. So we did the expansion of the Whittaker function near at infinity, right? And we computed the coefficients that you have to put on the area A and the area B, so that you match the exact phase up to an error of 1/h, let's say, or maybe even a bigger power. Yeah, of the true solution. So my G here, you see the way I wrote it has some prefactor that basically tries to compensate because I'm using the Lebesgue measure instead of the measure that I'm using. Has,
Between 102 and 103.
yes, I can do that. Is that enough? So these are the coefficients of the combination of areas that guarantees you that at infinity you are matching the phase. We did the computation, just computed the exact coefficients. So I can actually go even larger. And maybe we can compare. I'm not sure. Yeah, you see that.
So they are exactly on top of each other?
Yeah.
This is orange and blue.
Yeah, orange and blue, but you're seeing the same.
Plot
Yes.
the difference.
You want the relative error again?
So you can't divide. You can-
What I'm doing here?
I think there you want to do what you said, it's above the-
Yeah, what I'm not sure. Sorry, but I wasn't. Yeah, what did you say?
Yeah, go, I think B minus 5.
Replace the comma by a mark,
This one.
and then maybe working precision
Which one?
100.
So I would like to see what happens if I only say consider the area. This is I'm going to my concern somehow. You see the order now of the error. Somehow there is gonna be a shift on the phase.
Yeah, I'm confused.
Yeah.
G, Y, A, B, can you explain what is?
Yes.
What are the parameters of G?
So G is the combination of area A, area B. So the coefficient A is going to be the one that it's multiplying the area A, and the coefficient B is going to be the one multiplying the area B.
Was the thing that you had about.
Sorry?
So
Yes.
So
The-
these are the arguments that you're going to.
Exactly. These are the coefficients that are in the argument of my function G, which are the right coefficients so that you match that asymptotic behavior at infinity of the true solution.
Involve these complicated.
Yeah.
formula of-
Yes,
of-
yes,
of-
Yes. Yes.
But maybe when H goes to 0, you can say that capital B is 0 of H or maybe.
We can plot it, yeah. So you can do it here if you want. So you have the expression there. The two, so in blue the A, in orange the B, let's say from 0 to 0.1 or something like that. Of course, the oscillation is it's a lot. So what could we do? Don't control maybe,
or from 20.2 and then, yeah. Good, so we probably want to avoid zero.
So the A is almost.
So A is -1 and B is almost zero.
So B comes from area
B.
BI,
B, yeah.
that makes perfect sense, this picture, so AI dominates BI. And you see, if you use the fundamental system that Adam indicated in his talk, AI plus IBI,
Mhm.
AI minus IBI,
Right.
you will get some linear combination of those.
Right. So let me pick then, okay. So let me pick those coefficients that make complete sense by what you said, and let's see what happens if I combine these two areas, the area A and the area B. Let's try to see what happens near the turning point. I suspect that what's going on is what Adam said, that you need like a complex combination with an I. This is what I'm suspecting that it's gonna happen, because this would be consistent with my picture now that I think about it. So, and I'm going to the concern. So this is the full picture now. On blue, you were supposed to see the true solution, but it's matched with my approximations. Basically, you can barely see it. Maybe I can zoom more. Yeah, I don't know. Maybe you can
So
see better.
blue is matched by orange and then green.
Yes, exactly. So on green is this combination of the area functions, but I haven't taken the complex combination. I think that is going to be the key, because when we do this combination in the way I did it, which is just a real coefficient A times the area A, real coefficient B times the area B, what I get is this green curve that is exploding somehow in the region here.
That would never work. There you have the sticker, that's
Exactly.
the real fundamental is an AI comma BI, and to the right, AI plus IBI.
This is what we were missing.
No. So
No?
that I completely get, because in any case.
I'm sorry, I couldn't hear you. That.
No. So what you want to do is to be able to express them as a product. So you want to have something that doesn't equate to zero. So what you say is, if you want to upgrade an approximate solution to an exact solution, then I think it's right. But if you want to stick with an approximate solution, then it doesn't make any difference, because you would have a combination, and since both of them are real, the coefficient has to be real. And so then,
in the end, you do get something real, but you work with AI plus minus IBI times with, I don't know, one with H bar to the output times this error.
but but I think these are two. So there is, first you get an approximate solution, and then you upgrade it to an exact solution. And I agree that if you want to upgrade it in a multiplicative way, then this is it, because we don't want to force the zeros out. So you need to use
Exactly.
the system.
You can try and raise the zeros, that I don't know.
Yes, but at least at this level, if I understand, well, you're looking for approximate solution, but a global
Yeah.
approximate solution.
Yes.
So I think these are two different stages. And if you look for a global approximate solution, then
So
you're going to,
we have this
how you do it.
Yeah.
You need to take coefficient of a fundamental system,
Right.
and if your fundamental system is real, and if you want to have a real function, then either you will take real coefficient of, it will be the same coefficient, because.
So you're saying that as long as we're concerned with the global approximation, this is what it is, basically. This is the picture that I can
Well,
get.
I don't think there is a way to, like, this would not make the difference. So you can choose your thing, so you need to glue.
But then that confuses me a little bit, because how is it possible that, well, no, that could be, that I get this exponential growth that I don't want to see somehow. Yes, you're seeing the green curve is this combination of areas with my coefficients computed so that I match the behavior at infinity. So I go now all the way to the turning point, and I'm seeing that to the left of the turning point, at the scale in which Adam has a nice approximation, I'm seeing this, yes, this growth here. You are seeing it on the picture, that the green curve is growing. I can go, if you want, to the turning point. The green curve is the,
But the area functions are not really a super good solution when you get in the forbidden region, because you have this potential V that goes up. So if you don't account for it, then
right, but what I'm more like concerned a little bit is that somehow in the description that Adam told us in the morning, it's an area function times some prefactor, which is completely equivalent or has to be equivalent to our prefactor W, or somehow I think that they have to be on the same framework of what we are doing. So you're seeing that in my picture, this combination of area functions, when I try to match them, the area A and the area B, so that I have the right asymptotics at infinity, I have this problem of the growth of the area B on the left of the turning point. And somehow, if I think that this is completely equivalent to what Adam presented, I don't know, there's something that I don't quite see, that why do I get this?
Because
Or how is that has more or less, now I understand the B is growing, but why can you get it?
even the smallest numerical error will be magnified by BI. BI just grows enormously. And so when you match your vessel from 0, you will kill the BI because it gets a tiny coefficient.
From 0, I have no problem, but yeah.
I mean, I think, so what you present is capital B, which is the thing that comes in the coefficient of BI.
Yeah.
If you match to plus infinity.
Yeah.
So it is not 0, but it is small like H.
Right.
And so if you want to have the exact case, then you need to have that. But it is asymptotically 0, it is very small. But when you go to the turning point, then it's a small coefficient, but times something that grows exponentially. And so it's going to get very big.
Yeah, you can see that.
I think this is the difference that, so if you want to have AI, so only the area I, then you make an error of size H in the coefficient of the BI.
Yes, I agree. Yeah.
And so it is small, but you're going to pay it when you get close to 0.
So, yeah, what can you want?
Yeah, no, I think
Yeah, but
It's a way and maybe I misunderstood you better, but did you say the coefficient of BI is on the order of H bar?
yeah, so it is
No,
small.
it has to be on the order of E to the minus pi over 2H bar. It is much, much, much smaller because at H bar 3/2 where we match vessel with area, right? Think of the Arnold business. That's how I see it at least. If we normalize the oscillatory guy like you suggested to be of side 1 at infinity, then the derivative of the distorted Fourier in this phi will be from the order of e to the minus pi over 2 sigma near 0. That's why in the stationary phase, this will not matter. The initial segment won't matter. But it's extremely important that it remains very flat and small for a long time. Why? So that we kill the PI. Right.
Yeah, I'm not sure I see, but maybe there is one way to see this. So you have the exact capital B.
yes.
Can you get the expansion of the
Yeah.
if you plot log B, log capital B. So the question now is B as a function of H, is it exponential or logarithmic?
We can figure it out with the picture.
So if you put log B.
No, you have the expression for it. Let's go on. Yeah, no, it's easy.
Can you spot out? I don't know what you're saying, Harry. Sorry.
No, you want to understand the value of B.
Yeah, but I can plot the logarithm maybe, or what? Or what do you?
I mean,
I can do
so
this
you can
expansion.
If you put B and log B, functions of H, you should be able to see if it's exponentially.
There is something that it's not doing.
Because log B is complex.
Yeah.
So the real part. This is log, the real part of log B. So it's imaginary. But that confuses me a bit even more.
No, but then absolute value of B.
Yeah, well, let's see, yeah.
No, not of absolute value of B.
Second. So absolute of B. And log B.
And not of absolute value. Yeah. And we just want to get the sense of this time. Yeah. So B is very small and log B is.
So you got in 0.1 to 0.2.
So it is like
One thing is not that far. And then more the other one.
But I could do maybe. I don't think this is very useful.
No, that is also like more and more.
Right. Yeah, we only see the oscillation, that's true.
Sorry, what?
I just wanted to get an idea of how was this as a function of h, but yeah, it's just it's what we have here. It's purely oscillation.
But no, so I mean, I thought we agreed that at least B should go to 0 as h goes to 0. So B is the coefficient of the A reading at infinity. So
Well, but there is the measure. Well, somehow the normalization of the function. Maybe that's it. What you're.
I think that's true from here, but it's not true.
So the coefficient of A and B is always of size 1.
If you start on.
Yeah. But so then A, so there is just no goal. If you just use A.
Just use that every day, yeah.
Yeah. So this was the question that I had, that if we want the right phase at infinity, we have to pay with this AB.
But then I don't see,
That it's bad somehow at a certain point. But well, yeah. Yeah, maybe it's what Professor Schlag said, that you have to consider this complex combination. That somehow it's gonna fix it. Anyhow, in the old paper, they already have also estimates on the difference between the true eigenfunction and this ABA, right? And also the Bessel function. So we have some hope that maybe we have, I don't know if we need 3 different regions like at infinity. I don't know if we are gonna need that, like in this combination of ABA, ABB that I presented in my picture. Then the ABA maybe here near the turning point, which is good enough. And here the Bessel function that cannot go, I think, all the way to 1, but let's say to 1/2. So maybe that's enough, and then yeah, it would be a matter of checking if that's enough to put it on the green function, so we get the decay of infinity. Now that I think we have a pretty good approximation. So yeah, I would like to understand better, maybe sit a little bit and do the complex combination, because yeah, you see from my picture what I couldn't make sense, and I think this is what Benoit is still thinking. Is yes, exactly this thing here. That my combination of areas that somehow it's almost perfect at infinity has this problem near the turning point. Well, not exactly near, but to the left of the turning. But maybe this is something that we can discuss together.
Because the PI
That's gonna grow.
grows like
Yeah.
e to the zeta to the 3/2.
Right, but what I don't get is a small constant as you,
Yeah, but then in order to beat that, you would need a constant that is as precise as e to the minus h star to the minus 3.
this is what I don't have, that constant.
You have to be super exponentially exact.
Is that move from 0 basal to actually 0
That would be, for me, that's not a problem. From 0 to the turning point, yeah, that should work without a problem. That what I'm saying is that if I do come from infinity with these coefficients that are computed so that we match the phase, then yeah, it is what you expect because you have the ARB that is growing exponentially.
We really touch it, the error would be equal as we estimate this.
So can you give, again, so what does your solution look like? The exact one, from 0 to h by 3/2. I know that you can't keep the exact one in terms of decimal, but then decimal times 1 plus h bar times the small.
Right, so my prefactor, let's see what I have. It is this function here somehow, so
It's
yours,
the psi function, and psi is given by an integral equation, has to be given by some.
yeah, so it's gonna come from that formula there, and the s is coming from the integral equation. Right.
So what you have is an approximate solution. It doesn't solve the solution exactly.
But if he's asking about the s, that the s is somehow,
I think it's.
maybe I misunderstood you.
Upgrade it from an approximate solution to a true solution. Is that?
I'm sorry.
No question is, yeah.
The Volterra will control the error, and I think it would be nice if we have leading order your Bessel times a function which is between a half and 2 or something. Yeah, 1 plus something.
On this one, more.
Yeah,
The error is 1 plus O
plus sigma, 1 plus 3 or sigma h star, yeah, perfect. And that goes basically 50% into that window from 0 to 1, 50%, because we only need much smaller than that, because h bar to the 3/2 is 0.00 something. Yeah, perfect.
Yep, so, yeah, I don't know.
But that's it.
Maybe we can leave it.
Well, thank you.
Have you thought a little bit about the
Not much,
complicated
not much. This is what we